Hello everyone, I hope you're doing well. In this video, we'll be completing our problem 21 and that's the third part. In the previous parts, we have proved these three relations and we have also derived and proved the average internal energy of a harmonic oscillator to be equals to this expression. In this video, we'll be calculating the average energy and the standard deviation in energy for a two-level system with energies E and negative E. So in this part, we'll be doing the last thing. Since the problem was really lengthy, that is why it was split it into three parts. So let's quickly get started with finding out the average energy first and then standard deviation next. In this single video, okay, there is no more part. Let's calculate the average energy of a two-level system. We have two different energy states here, as they have told us in the question as well. Two-level system means there are only two different energy states. A system has one is positive E and the second energy state it has is negative E. All right, and we know that the average energy is given by average energy is given by here average energy and average internal energy, both of these terms are equivalent. That is given by following formula that we have proved as well. Okay, we can use this formula to calculate the average energy, and we can expand it into P1, E1 since there are only two states. So I is equals to 1 and 2. So I equals 1 and 2. P1 E1 plus P2 E2, whereas probabilities are actually equals to Pi equals e to the power E1 by kt divided by z, where z is the partition function. So if we put the value of P1 and P2 here, so it becomes e to the power E1 by kt, kbt or kt, that's same, into E1 plus E2, I'm writing E2 first, e to the power E2 by kt by z. So since the denominator is same, so we can take LCM and it's simply E1 e to the power minus E1 by kt plus E2 e to the power minus E2 by kt. This problem is actually this part of this problem is actually short and it wouldn't be lengthy. In now we are gonna put the value of E1 and E2 here, that we know is E and negative E respectively. So let's put these values. Instead of E1 we write e to the power minus E by kt, plus instead of E2 we'll write minus e to the power minus into minus E by kt divided by z. Z is the partition function, and we know that partition function is equals to summation over all states e to the power minus E I by kt. So it means since we have two states only, so it's e to the power minus E1 by kt plus e to the power minus E2 by kt. Okay, that's simply the partition function. It's like we find out this Boltzmann factor for all of the states that are available, and since there are only two states, so we'll write this Boltzmann factor for E1 energy state and then for E2 energy state. So we can write it here like that, and we need to insert the value of E1 and E2 here as well. So let's do that. E to the power minus E by kt plus minus minus, so it's minus e to the power minus minus plus, so it's power kt. Then here we are gonna put the value of E1 and E2 again, so it's instead of E1 it's E by kt plus e to the power minus into minus E, since E2 is minus E by kt. Okay, and let's simplify. Here E could be taken as common, and I'm taking negative E as common. I'll tell you the reason afterwards because it encloses a formula that I just wanna make. So that's why I'm taking negative E common, because I want to make this exponent with positive power, okay, this term with positive power to be positive. That's why I'm taking negative common as well from numerator. So E is also taken common, so it's e to the power e by kt left. I'm writing it first. Okay, this negative sign has changed into positive sign because negative was, taken common. I hope you got it, what I did. So here its positive sign will change into negative, and I'm gonna write this one term with negative power next. Okay, and since e was taken common, so that is why I'm not writing e with them, divided by e to the power minus e by kt plus e to the power minus minus plus, so this power becomes positive as well. All right, now this thing inside of these brackets encloses a formula for tan hyperbolic of power. What is the power here? E by kt. Okay, positive number is taken, so it encloses a formula for tan hyperbolic of e by kt. I'll paste the image of those formulas for hyperbolic function on the screen so that you can have a reference. But let me write the general formula here for you. Tan hyperbolic of x, let's say there is x, is equals to e to the power positive x, okay, minus e to the power negative x divided by e to the power positive x plus e to the power negative x. That's the formula for tan hyperbolic of x in terms of exponentials. Okay, so that's why I took negative as common, so that this thing with positive power becomes positive. Okay, and in the denominator both of them were positive, so there was no need to do any shifting. But in numerator there was a negative sign extra, so I took it common. Okay, so that's the internal energy or average energy of a two-level system. Now, so next we are going to find out the standard deviation in energy of a two-level system. So the formula that we are going to use is the same that is mentioned in the problem statement, so there is no worry about which formula to use. Okay, so let's use that formula which we proved as well. And we had this formula for, we know that the standard deviation is given by, we know that standard deviation in energy, deviation in energy is given by the one mentioned in the question as well. This was the formula, pi ei square minus u bar square. U bar is already known, so we can directly insert the value right back into the equation. And yeah, that's the formula for standard deviation that we'll be using. So let's first calculate this part here, and then we'll insert it right back here because that's something that needs to be calculated overall. Pi ei square, so we can see that we have only two states. One is positive e and the other is negative e. We can expand it. E1, I'm just gonna write e first. Okay, e1 square p1 plus e2 square p2. Let's put the value of p1 as well, e to the power minus e1 by kt by z plus e2 square e to the power minus e2 by kt by z. E1 squared e to the power minus e1 by kt, I'm taking LCM so that we have a common denominator which is z, and we know the value of z as well, so let's put the value here and then we'll insert the value of e1 and e2 simultaneously. E1 by kt plus e to the power minus e2 by kt. Okay, instead of e1 I'm gonna write e square e to the power minus e by kt plus, instead of e2 we'll write minus e whole square e to the power minus into minus e by kt divided by e to the power minus e by kt plus e to the power minus into minus e by kt. Okay, next e square e to the power minus e by kt and minus e into minus e, it's like minus e square, so it will become positive as well because square of a negative number is always a positive number. They multiply themselves to make it positive, so the power become positive in the numerator as well. E to the power e minus minus plus, so it's e by kt. We can take e squared as common, so taking it common, and we are left with this value. In denominator we have this thing, e by kt. Okay, this cancels out. What a relief. That's such a big relief, I must say. Okay, that's e squared that is left now, and we can put it back into this equation, and we'll insert the value of u bar square as well, so that there will be some simplifications and we'll get a result. Let's insert the values. So from 1, you can name it depending upon the equations you have previously, because I believe that in part 1 and 2 we have already named equations as 1 and 2, so you can use a different number for it. P and I, ei square pi minus u bar square. It's e square minus, instead of u bar we will put its value, which was negative e tan hyperbolic of e by kt whole square. We can open the square. It's e square, negative vanishes, e square tan square hyperbolic e by kt. Taking taking e square common, it's 1 minus tan squared e by kt. Okay, and we have trigonometric relations that will tell us that what is 1 minus tan square hyperbolic of e by kt. Okay, let me see in internet. Then I'll get back to you. And there will be square on the h. Okay, we'll write square on h, and that is equals to secant hyperbolic square e by kt. So we'll write it like that. Delta u square equals e square 1 minus tan hyperbolic square e by kt. Okay, you are supposed to write it like that. Then e square, we call it as hyperbolic trigonometric identities. So secant hyperbolic square e by kt brackets delta u square, that is the standard deviation in energy for a two-level system. Okay, and the average energy was equals to this term. That is it for this problem. I hope you enjoyed it. And like, share and subscribe. And I'm planning to upload more of these videos, like from chapter 4 of Introduction to Statistical Mechanics by Roger Bole, and there are a ton of other problems that I'm planning to upload from different chapters. So if you want me to upload some specific ones, you can ask me. And yeah, that's all from my side. I request you all to share these videos and channel as much as possible. This will help me a lot. And thank you. Goodbye.